4.5 practice problems. If 0.4 moles of hydrogen and 0.15 moles of oxygen were to react completely as possible to produce water, what mass of reactant would remain? So they did not give us the equation, so we are going to need to write out the equation. So we have hydrogen being added to oxygen going to water. This equation is not balanced. Now it is. We are looking for the mass of the reactant that is going to remain, which means that we are going to have to figure out who the limiting reactant is. Now the ratio between hydrogen and oxygen is 2:1, so we can see that we do not have enough of the oxygen to react fully with the hydrogen. So we can go ahead and figure out how much we should have left over. So if this was to react fully, this would be 0.2. This is 0.15. So this is our limiting reactant here. So we just need to figure out how much that is actually going to produce. So looking for the moles of water that we can produce from 0.4 moles of hydrogen. Just a simple mole-to-mole calculation here. Mole of hydrogen to mole of water is going to be a 2:2 or a 1:1 relationship here. So for every 2 moles of hydrogen, there is 2 moles of water. 2/2 simplifies to 1/1. So that's basically just going to be 0.4 moles of water that could be produced from the excess reagent. Now we'll figure out how much is actually produced based off of our limiting reagent. Which, if you didn't know that this was going to be the limiting reagent, this is also how you would figure out that it was going to be the limiting reagent, is just by doing this simple calculation to begin with. So 0.15 times 2 divided by 1 gives me 0.3 moles of water that would be produced. The difference here is going to be how much I was not able to produce. So 0.1 moles of water worth of hydrogen is not used. Since we know that the relationship is 1:1 or 2:2, that means that 0.1 moles of hydrogen were not used. And we want the mass of that. So the number of grams of hydrogen that are left over from 0.1 moles of hydrogen our molar mass of hydrogen. Hydrogen has a mass of 1.008, and there are 2 of them in H2. So that's going to be 2.016 grams of hydrogen per 1 mole of hydrogen. Moles of hydrogen cancel. 0.1 times the 2.016 gives me 0.2016. I only get to keep 2 sig figs, so that is just 0.20 grams of hydrogen, which is option choice A. When 8 grams of N2H4, which has a mass of 32 grams per mole, and 92 grams of N2O4, which has a molar mass of 92 grams per mole, are mixed together and react according to the equation above, what is the maximum mass of water that can be produced? So this is again going to be a limiting reagent problem. So you are going to find the mass of water that can be produced from both of these. So X grams H2O from 8 grams of the N2H4. Molar mass of that, 32 grams. N2H4 per 1 mole, N2H4. And then the mole-to-mole relationship between N2H4 and H2O. We have 2 moles of N2H4 per every 4 moles of H2O. So 8 times 4 divided by 32 and 2 gives me 0.5 grams. No, it doesn't. I was looking for the mass of water and I stopped at moles of water. My apologies. Okay, currently in moles need the mass, so we have hydrogen's mass at 1.008 times 2 plus oxygen's mass at 16, so that gives me 18.016 grams of water per every 1 mole of water. This is why it's really important to state what you are looking for so that you don't accidentally do what I just did. So we will have 8 times 4 times 18.016 divided by 32 and 2, and that gets me 9.008 grams. And then we need to do basically the same thing, but for that mass of the N2O4. 92 grams, N2O4. Okay, molar mass is the same, so this is basically 1 mole. Okay, the relationship between N2O4 and water is a 1-to-4 relationship, so there's 1 mole of N2O4 for every 4 moles of water. We're not going to make the same mistake that we just did. We're going to go ahead and multiply it by the molar mass of water here, so 18.016 grams of water per 1 mole of water. Okay, plug that in. So we know 92 divided by 92 is going to give me the same answer. So all I need to do is do 4 times 18.016. Which gives me 72.064 grams of water. Unfortunately, that is substantially more than what we were able to create with the N2H4. So option choice A is going to be my answer, since that is the mass of water that I could produce with the amount of N2H4 that I have present, and therefore that is the only amount that I can actually produce. I can't produce any more than that. I don't have enough of the reactant to do so. According to the reaction presented above, how many grams of aluminum, atomic mass of 27, are necessary to produce 0.5 moles of hydrogen gas at 25 degrees Celsius and 1 atmosphere? So we are going to go ahead and figure out how many grams we need to produce 0.5 moles. So grams of aluminum are needed for 0.5 moles of hydrogen. Relationship between hydrogen and aluminum is a 3-to-2, so 3 moles of hydrogen gas per 2 moles of aluminum. And then the molar mass of aluminum was given as 27 grams per mole. And that's going to go ahead and give us our answer. So 0.5 times 2 times 27 divided by 3 gives me 9 grams of aluminum being needed to produce that amount of hydrogen. What mass of gold is produced when 0.05 moles of gold 3 sulfide is reduced completely with an excess of hydrogen? Okay, they didn't give us the reaction, but they did tell us everything that we need to know. So we know that gold is going to be produced when we react the gold 3 sulfide with hydrogen gas. So the hydrogen is going to be my cation here. And gold is going to be produced. Then I need to go ahead and balance my reaction. Okay, now that we are balanced, we can go ahead and move forward. So I'm looking for the grams of gold from 0.05 moles of the gold 3 sulfide. Okay, mole-to-mole relationship is 1 to 2, so for every 1 of the gold 3 sulfide, there's 2 moles of gold. And then I need the mass of gold. So gold has a mass of 196.97. Okay, so 0.05 times 2 times 196.97 gives me 19.697, and then I get 3 sig figs, so rounding up, that gives me 19.7 as my mass. In the reaction represented above, what mass of hydrofluoric acid is produced by the reaction of 3 times 10 to the 23rd molecules of hydrogen in an excess of fluorine? Assume the reaction goes to completion. So we have our balanced reaction here. We have molecules, which does mean that we are going to be using Avogadro's number. So we are looking for the mass of the hydrofluoric acid that will be produced by 3 times 10 to the 23rd molecules. I like to shorten it to particles just because particles can be shorthanded as part versus molecules, which can't really be shorthanded because it looks like moles. Particles of hydrogen. So I need to go ahead and get out of particles and into moles. So I'm going to use Avogadro's number, which is 6.022 times 10 to the 23rd particles or molecules per 1 mole. Then out of moles of hydrogen into moles of hydrofluoric acid, the relationship is 1 to 2. So for every 1 mole of hydrogen, there is 2 moles of the hydrofluoric acid. And then I need the mass of that. So hydrogen has a mass of 1.08, fluorine has a mass of 19, so that's going to give me a mass of 20.08 grams of hydrofluoric acid per 1 mole of hydrofluoric acid. And I can go ahead and plug that into the calculator. So 3 times 10 to the 23rd times 2 times 20.08 divided by 6.022 times 10 to the 23rd gives me 19.9. Now I only get 2 sig figs, so this is going to round up to 20 grams. A 6 mole sample of C3H8 and a 20 mole sample of chlorine are placed in a previously evacuated vessel where they react according to the equation above. After one of the reactants has been totally consumed, how many moles of hydrochloric acid will have been produced? So this is going to be a question about limiting reagents, so we need to figure out who the limiting reagent is. Now, the relationship between the hydrocarbon and the chlorine is a 1 to 4 relationship. So I can see that my limiting reagent is going to be chlorine because I would need this times 4. Okay, so that would get me up to 24 moles as an equal relationship between the two. So this is going to be my limiting reagent, and so I can just go ahead and figure it out from there. Now, I see the relationship between chlorine and the hydrochloric acid is a 1-to-1 relationship, and so if I completely react all of the chlorine, then I am going to get the same amount of chlorine or hydrochloric acid that's going to come out. So since I put in 20 moles of chlorine, I should get out 20 moles of hydrochloric acid. N plus is an unknown metal cation with a charge of +1. A student dissolves the chloride of the unknown metal, MCl, in enough water to make 100 milliliters of solution. The student then mixes the solution with an excess of silver nitrate, causing silver chloride to precipitate. The student collects the precipitate by filtration, dries it, and records the data shown below. The molar mass of silver chloride is 143 grams per mole. The mass of the unknown chloride is 0.74 grams. The mass of the filter paper is 0.8 grams, and the mass of the filter paper plus the silver chloride precipitate is 2.23 grams. What is the identity of the metal chloride? So looking here, I can go ahead and convert this into a more usable number. So I need to go ahead and subtract 0.8 from the mass of the silver chloride precipitate plus the filter paper, because I don't care about how much the filter paper weighs. So my mass of the silver chloride precipitate is going to be 1.43 grams. And then I can go ahead and figure out how many moles of chlorine are going to be in here, and that will get me able to go ahead and figure out how many moles of chlorine are in my mystery metal compound and help me figure out what my overall mass should be. So we are looking for the number of moles of chlorine here, given 1.43 grams of silver chloride. So I need to go ahead and use the molar mass of 143 grams of the silver chloride per 1 mole of silver chloride. And then the relationship is 1-to-1. So for every 1 mole of silver chloride, there is 1 mole of just the chloride there. So 1.43 divided by 143 gives me 0.01 moles of chlorine. The mass of that chloride, chlorine has a mass of 35.45. Okay, and so the mass that is coming from the mystery metal chloride, 0.3545 grams of that is coming from the chloride. So 0.74 minus the mass that's coming from chloride will give me a mass of 38, or 0.3855 grams. Remember that this is, we're looking for something that would be approximately that mass. So we're looking for a metal that has approximately this mass when we multiply it by that 0.01. So we have lithium, which is much too small. We have sodium, which is at 22. We have potassium, which is at 39, pretty close. And then our last option is going to be copper at 63. Since the potassium is the closest mass there, we're going to go ahead and choose potassium as our mystery metal. What is the maximum number of moles of aluminum oxide that can be produced by the reaction of 0.4 moles of aluminum with 0.4 moles of oxygen? So this is going to be a limiting reaction. limiting reactant problem, we need to go ahead and write out the reaction and balance it to see how it's going to go. So once we have that balance, I can see that I need more aluminums than oxygen. So aluminum is going to be my limiting reactant here. And so I can produce, the relationship is 4 to 2 or 2 to 1. So I can produce half the amount of aluminum oxide as I have aluminum. So 0.4 divided by 2 gives me 0.2 moles. Permanganate and oxalate ions react with an acidified solution according to the balanced equation above. How many moles of carbon dioxide are produced when 20 milliliters of acidified 0.2 molar potassium permanganate solution is added to 50 milliliters of a 0.1 molar sodium oxalate solution? Okay, so first up, I need to go ahead and figure out how many moles I have present in each of these. So 20 mils is 0.02 liters, and 50 mils is 0.05 liters. And I can go ahead and now multiply that to figure out how many moles I have present. So 0.05 times 0.1 molar gives me 0.005 moles of the sodium oxalate. And 0.02 times 0.2 gives me 0.004 moles of the potassium permanganate. Okay, so I am figuring out how many moles of carbon dioxide I can produce. So the relationship here, I am looking at my mole-to-mole relationship between the oxalate and the permanganate here. So the permanganate to carbon dioxide, I have 2 to 5. So that means I can produce 5 times the amount that I have here. And the oxalate to the carbon dioxide here, I have 1 to 2, so I can produce 2 times as much there. So this times 2 is 0.01 moles of carbon dioxide. This is 0.02 moles of carbon dioxide. I have to choose whichever I have less of. I have less of the, I can produce less from the oxalate, so that means that that is going to be the amount that I am able to produce.